All right. So oftentimes when we have a mathematical model that models some phenomena, we're interested in finding the maximum or the minimum of that function. So for example, if a function models revenue, maybe we want to maximize revenue. So we would like to know, when is the revenue maximum? Or maybe it models cost and we want to know what, where the cost is the minimum. So that's what we're going to look at today, is we're going to look at maxima and minima. And so maxima, this is just a pluralization of maximum. Minima, that's just a Latin pluralization of minima. And both of those together are called extrema. Okay, which kind of makes sense. They're like the extremes, right? The maximum and the minimum are the extremes of a function. So extrema is any point where the value of the function is largest or smallest is called an extrema. Okay. Now we're going to look at two different kinds of maxima and minima. Now, oftentimes we're interested in a global maximum. We want to know what's the overall maximum of a function. That would be called a global maximum. Or maybe we're interested in the overall minimum. That would be a global minimum. We're going to get to that. Today we're just going to focus on local maxima and minima. So a local maximum minimum is just, let's just start with here, the local maximum. A local maximum is just a point on the function that's larger than any of the points around it, nearby. Okay, so we're just comparing it to its neighbors. So, for example, this is a local maximum. So down here, a local minimum is kind of the same sort of thing, only now we're looking for where the point on the function where it's smaller than any other points near it. So those are local. That's a local maximum. That's a local minimum. But this point here is also, right? This is also a local maximum. Okay, just because it's larger than any of the points nearby. Okay, over here we have another local minimum. Okay, just because it's smaller than any of the points near it. Now these global maximum and global minimums are also local, right? Because any of the points near it, are smaller than that point. So this is also a local maximum. Local maximum. Okay, and this is also a local minimum. Okay, now you can see minimum that there can easily be more than one local minimum, right? You can see here we have 1, 2, 3 local minima in this function. Okay, we've also got 1, 2, 3 local maxima. So oftentimes there's more than one local maximum or minimum in a function. Okay, now the global or absolute maximum would be the point on an interval that's larger than any other value on that interval. Okay, and the same way with a global minimum. A global minimum is just kind of the overall minimum of the function. We're actually going to talk about these things in 10.3. So today we're going to focus on local minima and maxima. Okay, so let's take a look at this example here. We just want to identify the extrema. So this is just kind of an example, just using the vocabulary that we just used. So you can see that the function has a local maximum right here, right? Because it's this point right here is larger than any of the points near it. Okay, so we can say that the function has a local maximum of 62 at x equals 2 on this interval between 0 and 7. Okay, down here we can say this point down here is a local minimum. The minimum value is 35 when x is equal to 5. Okay. Now we also have, we can find the global maximum. Now, when we find local maximum or minimum, those points are not necessarily the global maximum. They oftentimes are global maxima or minima, but sometimes we also have to check the endpoints. Okay, so like for example here, if we're modeling this, whatever this function represents, the maximum is actually here at 87. The maximum is 87 at x equals 7 at the endpoints. Okay, and here the global minimum is 10 at x equals 0. Okay. All right, so that takes care of some of the vocabulary, but let's now look at this function from a calculus perspective. Okay, so if we think about the derivative of this function f of x, you can see that, okay, so remember the derivative is just essentially the instantaneous rate of change or the slope of the function at any given point. So you can see this function is increasing, 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 right? The slope is positive until you get to this point right here at this local maxima where now it's changing direction, right? It's changing direction and becoming a decreasing function. So at this point where the local maximum occurs, the derivative is 0, right? So f prime of x equals 0 at that point. And then it becomes a decreasing function until we reach this local minimum point. And you can see at that point the derivative is 0. So f prime of x equals 0 at that point. Okay? And then it becomes an increasing function. Boom, boom, boom. Right? So that gives us a clue as to how to use calculus to find these local minima and maxima. So let's take a look at this next thing. Okay, so recall what I just said is that the derivative is the instantaneous rate of change or the slope of a function. If the derivative is positive on an interval, then the function is increasing. If the derivative is negative on an interval, then the function is decreasing. Okay, this is all review. We can also look at the second derivative of a function. Okay, if the second derivative is positive, then the slope is increasing, and we call it concave up. Right? The graph is concave up. If the second derivative is negative on an interval, then the slope is decreasing on an interval, and the graph is concave down. So this just gives you a little bit of a visualization of what a graph looks like when it's concave up and decreasing. Okay, you can see it's decreasing. So this would be like a curve of a function. You can see it's decreasing, but it's decreasing at a slower and slower rate, right? So it's concave up, okay, because you can see the slope is negative, but it's becoming less negative as you come down here, okay? Now here it's increasing, so the slope is positive, okay, but it's increasing, right? It's becoming more and more positive. Okay, so here's a case where you concave down and increasing. So you can see it's increasing, right? The slope is positive, but it's concave down because the slope is becoming less and less positive, right? And then this curve represents something that would be concave down and decreasing. Okay, you can see it's decreasing, the slope is negative, and it's concave down because the slope is becoming more negative. Okay, so it's a steeper slope, but it's more negative. So it's the slope is increasing in the negative direction, right? Which gives us gives us a second derivative that's less than 0. Okay, so the trick to finding local extrema with calculus is to first of all just identify candidates. And as you saw, back here, our candidates, it seems obvious to look at the places where the derivative is 0. And so that's how we identify the critical points. Okay, so a critical point is a point on in the domain of the function where the derivative is 0 or the derivative is undefined. Okay, so we have a couple different criteria for identifying critical points. Okay, now we are going to primarily be looking at continuous functions. So, all right, anyway, I was going to use a highlighter. Okay, we have 2 criteria. All right, here's one criteria. Here's the other. All right, either where the derivative is 0 or the derivative is undefined. Okay, now we're going to primarily be looking at continuous functions. So the second criteria really won't, for the for the problems we're going to run into, we're not going to really be too worried about where it's undefined, but it's important that's an important thing to remember. So basically it comes down to, if we find where the derivative is 0, and those would be our critical points of the function. Now there's some vocabulary here too. A lot of times when we refer to a critical point, we're talking about the x value, right? The point in the domain. So we're just talking about the x value, but it also could be the coordinates, the 2 coordinates, the x and the y value. You could refer to that as also the critical point. Okay, and then the critical value is the value of the function at the critical point. Okay, so that's just some vocabulary. All right, so let's take a look at this next example. We're just going to identify the critical points and critical values for the following function. All right, so we have a nice, simple little polynomial, and in order to identify the critical points, we're just, first of all, just going to take the derivative. All right, so we're going to find the derivative of this function with respect to x. All right, so we're just going to use the power rule. So we get 3x squared minus 18x minus 48. Okay, now we want to find where the derivative is 0. So it would probably be a good idea to factor this thing. So the first thing I'm seeing is always this factor of 3. It's easier to work with smaller numbers. So I'm going to first of all factor out a 3. Okay, and then I have that. Now let's factor this quadratic here. Okay, so I'm looking for factors of negative 16 that add to negative 6. So we're going to have x minus 8 and x plus 2. Okay, so that tells us that the critical points are, when the first derivative is 0. So that gives us critical points at x equals negative 2 and x equals 8. Okay, so those could be considered our critical points. Now our critical values are the values of the function at those points. So critical values, okay, we're just going to put those numbers into the function. Now if I put in negative 2, so negative 2 cubed minus 9 times negative 2 squared, when I do that, I'm just going to do that at my calculator. I got 104. Okay, and when I evaluate the function at 8, I get negative 396. Okay, so those are our critical values. Now we could also refer to the critical points by their coordinates. Critical points. Okay, so we could also consider the critical points to be negative 2, 104, and 8, minus 396. Okay, either way. Now, typically, we're going to just use this definition of critical points, where it's just the x values. Okay, it depends on the problem, what they ask for, and what you need to know. So, let's go on. So here's the first derivative test for finding local minima and maxima. So what you're going to do is you find the critical points, and then you evaluate the first derivative on either side of those critical points. All right, and if the derivative, okay, so we're evaluating f prime, right? The derivative of f. If the derivative of f goes from negative to positive, that means that the function is going from decreasing to increasing, right? And that's the case where we're going to have a local minimum. Now, if the function is going from increasing, where the derivative is positive, to decreasing, then we're going to have a local maxima. Okay. Now, you do get cases where neither of those things occur. You might have a situation where you have a function that's going, or you have a first derivative in here that's 0, but it's increasing, and then it's still increasing. Okay, so you can have a situation here where you have a critical point. So this would be a case where you have a critical point, but it's neither a maxima or minima. Okay, so we're looking for spots where the function goes from decreasing to increasing, or increasing to decreasing. All right, so let's take a look at that same function that we had before here. X cubed minus 9x squared minus 48 plus 52, 48x. All right, so let me just scroll down here. All right, so from example 2. All right, from example 2, we found that the derivative of that function, that polynomial, and I'm just going to write it in factored form, x minus 8 times x plus 2. Okay, that was our derivative, and we had critical points at x equals negative 2 and 8. Okay, so we need to evaluate the derivative of the function around these critical points. So what I'm going to do, I'm just going to draw a number line that represents the domain of the function. Okay, and I'm going to mark the critical points, 2 and 8. Okay, now I want to know what's happening to the function around these critical points so that I can figure out whether it's a local maximum or a local minimum. So I'm going to test some points. So these are my critical points, and I want to look at this interval. I'm going to start by looking at this interval right here, where x is less than, oops, this is supposed to be negative 2. X is less than negative 2. So let's test a point to the left of negative 2. So I'm going to test points. Okay, so let's start out by testing f prime of negative 3. Okay, I want to know what is the value of the derivative on to the left of negative 2. So I'm just going to put negative 3. So I put that into my function. All right, so negative 3 minus 8 is negative 11. And then negative 3 plus 2 is negative 1. So I get a positive 33. Okay, that's greater than 0. So what that's telling me is that to the left of negative 2, I have a positive slope. So f is increasing, right? Because the slope is positive. So I'm just going to draw, and I'm going to indicate that with a little up arrow. Okay, so I have an increasing function to the left of negative 2. Now let's go to the next interval between negative 2 and 8. And an easy point to test would be 0. So let's just put 0 into our derivative and see what the slope is looking like between negative 2 and 8. Okay, so if I put in 0, I get negative 8, and then we have plus 2 times 2, right? So when I multiply that out, I get a negative 48. Now that's obviously less than 0. So what's that telling us? That's telling us that the slope in between negative 2 and 8 is decreasing. So the slope is negative, so the function is decreasing. So f is decreasing. Okay. So now I know that if I were to graph the function, the actual function, not the derivative, the function, it would be a decreasing function. So I'm going to indicate that with a little arrow. Okay. And now we have one more interval to test. So I'm going to look at the derivative somewhere to the right of 8. Okay, so I'll just pick up a 10 because 10 is easy to work with. So 3 and times 10 minus 8 is 2, and 10 plus 2 is 12. When I multiply that out, I get 72, and that's greater than 0. So the function is, right, the slope is positive, so the function is increasing. Okay. All right, so now we have to decide. We have these critical points. We have to decide, are they local minima or maxima? Well, I'm going to first, I guess I have to indicate. I'm going to indicate my increasing function here to the right of 8 with a little arrow going up. Okay, so you can imagine, I'm just indicating that on the number line. And if I actually drew it, I'd have something that's increasing, decreasing, increasing, right? So increasing, decreasing, increasing. So here's 2 and here's 8, not to scale. So you can see that f of x, the function, has a local maximum of, now we've already calculated what the values are in the previous example, so we found that the value of the function at negative 2 was 104 at x equals minus 2. Okay, and also the function has a local minimum, minimum of, and we already calculated this value in the previous example, 396 at x equals 8. Okay, so we've tested we found our critical points, and we tested intervals on either side of those critical points in order to determine whether those critical points were local maxima or minima or neither. Okay, in this case we got one local maximum and one local minimum. Okay, so one thing to watch out for, warning, 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 right? Not every critical point of a function is a local maxima or minima. So let's take a look quickly at this function f of x equals x cubed. So the derivative of that function is equal to 3x squared, right? It's using the power rule. And if I set that equal to 0 to find the critical points, I just have one, right? We have a critical point at x equals 0, right? Now, if I test the intervals, so I have, I can draw my little number line representing the domain of the function, right? And here's 0. If I test a value to the left of 0, for example, f of f prime, I want to evaluate the derivative at negative 1, okay, that's to the left of 0. I put in negative 1 into my derivative, not the original function, but the derivative, because I want to look at what is this function increasing or decreasing at that point, right? So I put in negative 1. Negative 1 squared is positive 1 times 3 gives you positive 3, right? So that's greater than 0. So that means it's increasing, right? Now, to the left of 1, if I put in, say, f of 1, right, just to test f, not f of 1, f prime of 1, testing the derivative to find out whether it's increasing or decreasing, and I put in positive 1, I also get 3. So that's also greater than 0. So it's still increasing. Okay? So in this case, it's increasing and then it's still increasing. So we do not have a maxima or minima. Now, if you were to actually graph x cubed, you've probably seen a graph of x cubed. It looks like that, sort of, right? So this is f of x equals x cubed, right? This is x. And you can see that, I draw that really, the slope is 0 here at 0, right? That's what our derivative told us. But it's not a maxima or minima, right? It's neither, okay? So we don't always get a maximum or minimum at every critical point. All right. Now there's also something called the second derivative test, which utilizes the concavity of a function to help us determine whether a critical point is a maximum or a minimum, local maximum or minimum, okay? And it makes sense. Concave up, I always think it's, the slope is increasing, right? It's either becoming more positive or it's becoming less negative. So the slope is increasing. And you can see this is sort of the shape of a concave up curve looks like. And if the value of the function at the critical point is greater than 0, meaning it's concave up, then we're going to have a local minimum. If the value of the function at the critical point is less than 0, which means it's concave down, then you can see we're going to have a local maxima. So, and if it's neither positive or negative, which would mean it's 0, then it doesn't tell us anything. Okay. So there's also a second derivative test. So let's apply that to this example 5 here. It's the same function that we've been working with. X cubed minus 9x squared minus 48x plus 52. We found that it has critical points at -2 and at 8. And now we're going to apply the second derivative test. So let's go back. So our derivative is as a polynomial. It's really easy just to find it. So it's 3x squared minus 18x minus 48. Okay. Now it's much easier to take the second derivative when the first derivative is in a polynomial form. So I'm just going to leave it like that. I'm not going to use the factored form like I had before. Okay, so the second derivative is just the derivative of the derivative. So if I do the second derivative, I get 6x minus 18. All right. So now, by the second derivative test, what I want to do is I want to evaluate these critical points against, with the second derivative. So I'm going to look at the second derivative at -2. Okay, because that's going to tell us the concavity. Right, so if I put -2 into my second derivative, I'm going to get -12 minus 18, and that gives me a -30. So that's telling us that it's concave down. Okay, concave down, boom, looks like that. So what that's telling us is that there's a local maximum at x equals -2, right, by the second derivative test. We can also apply the second derivative test to our other critical point. Right, so put in 8. 6 times 8 is 48. Minus 18 gives us a positive 30. So it's concave up, right, because it's a positive second derivative. So concave up tells us that we have a local minimum. at x equals 8. All right, pretty cool. Let's keep going here. All right, so here we're given some information about a function. We're asked to sketch a graph of this function. So I'm first of all just going to draw my little number line of the domain. Okay, we have critical points at 2 and at 5. Okay, and we're told that the first derivative is positive to the left of 2. So that's telling me it's increasing. Okay, so I'm going to indicate it that way. And it's also positive to the right of 5. Okay, so we have increasing. An increasing function. The first derivative is negative between 2 and 5. Okay, so I'm going to show it as it's decreasing between those two values. Okay, so that gives me, I mean, just looking at that, I can kind of tell what the shape of the function is going to be. Now, I can't actually draw this function with any kind of accuracy because I don't have enough information. But what I do know is that it's going, let's see, I mean, 1, 2, 3, 4, 5. Okay, I'm just going to, oops, here's 2 and here's 5. All right, so I know it's going to have a maximum at 2, right, because it's increasing. The derivative is 0 because it's a critical point, and it's going from increasing to decreasing, so it has to be a maximum. Okay, so I'm just going to draw something, draw a point, just a random point. So it's going to go through, let's put it there. It's going to look like that, and then it's decreasing until we get down to some point, I don't know, just say here, at 5, we're going to have a local minimum. And it's going to go back to increasing. Okay, so this is just the general shape of f of x. Okay, now this is, I have no idea what the magnitude of any of these points are because I don't have enough information. All I know is I have a local maximum at x equals 2, and I have a local minimum at x equals 5. Okay, but this graph is not unique, all right? This graph is not unique. There's not one answer to this problem. I could have drawn something that looks like this, right? Could look like that. I don't know how far up these values are going. I could go way up here. Oops, that's okay. Getting a little crazy there. All right. Anyway, you get the idea. This graph is not unique because I really don't know what the magnitude of these points are. All I know is what's happening with the derivative. So I know that's just the general shape of the graph. All right. Let's look at another example. Okay, so here we have the value of an investment at time t, and then we're calling it s of t. And with the graph we're given here, though, is of the derivative. So this is something you got to be careful of because it's really easy to see this graph and think, oh, that's my value of the investment. But no, this is the rate of change of the investment. Okay, so watch that carefully when you're doing your homework. So we're given a graph of the rate of change of the value of this investment over time. We're asked to find out where the critical points are, identify the critical points as local maxima, minima, or neither, and explain what the financial significance of this is. All right, so because we're given the derivative, remember the critical points are where the derivative is 0. Okay, this is the derivative. So these points right here at 1 and 4 and 6 are our critical points. So we have, I'm just going to answer part A right up here, right? Because I want to keep everything near the graph without having to scroll down too far. So S prime of t is equal to 0 for x equals 1 and 4 and 6. So these are our critical points. These are the critical points. Okay, So that's easy enough. All right, now we want to figure out, we want to identify these critical points as either maxima, minima, or neither. So what I'm going to do, I'm going to draw my little number line here. Okay. And so let's say this is 1. All right. 2, 3, 4, 5, and 6. Okay. So those are my critical points that I've marked here. And I want to look at whether the derivative is positive or negative. So I'm basically just looking at where is it above the x-axis, or in this case the t-axis, and where is it below. So you can see between 0 and 1 here in this segment right here, okay, you know, the derivative is positive, right? So to the left of 1, it's an increasing function. Okay, I should make these a little darker. There are critical points. Okay, so it's increasing to the left of 1, right? Because the derivative is positive. Now, it's also positive between 1 and 4, right? It's also positive in here, right? It's above the x-axis or the t-axis. So it's still increasing here between 1 and 4. The only place where it's negative is here between 4 and 6. Between 4 and 6, it's decreasing, right? Because the derivative, remember this is the derivative, the derivative is negative, so the function itself is decreasing, okay? And now, on to the right of 6, we're back in the positive, into positive rate of change, all right? So it's an increasing function to the right of 6. Okay, now we could actually, if I could actually draw my S of t axis, and I could try to sketch this graph, and it's not asking me to do that, but you can see here we have it's increasing, right, to the left. I'm just going to kind of draw here. It's increasing, but then it flattens out because we know this is a critical point, right? So the slope right here at 1 is 0, but then it keeps increasing, so it slows down. It becomes 0, but then it keeps increasing. So never actually dips down and goes negative, okay? So then it's increasing, 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 increasing until we get to 4. Let me draw that in there, okay? Till we get to 4. And then it goes from an increasing to a decreasing function, okay? And then it's decreasing, decreasing, decreasing till we get to 6. And then it starts increasing again. So the slopes here of the function itself at 6 and 4 are both 0. That's indicated over here, you know, in the graph of the derivative. Okay, so you can see it's increasing, it flattens out, but then it keeps increasing, and then it starts decreasing and then increasing again. Okay, so that just gives us an idea of what our actual function looks like, because we are only given the derivative. All right, so let's identify these as these critical points as maxima or minima. And yeah, actually, now that I've drawn this, it's pretty easy to figure out that this has to be this point at 4. We have a local maximum at t equals 4, right? Oh, oops. Yeah. T equals 4. Yes. Right, because our derivative is going from positive to negative, right? Going from positive to negative slope. So we have to have a local maximum there. We're going to have a local minimum at t equals 6, right? Because our slope is going from negative to positive. Okay, we go from decreasing to increasing, so we have a local minimum. And then the only other critical point is at 1. And so at t equals 1 is neither a local maximum or minimum. Okay. T equals 1 is neither, because we went from increasing and then we're still increasing. So we're not going to have a max or a min at that point. Okay, so that takes care of, that's actually part B. This is identifying each of the critical points. All right. So now we just have to interpret this in terms of, the value of an investment. This S function is the value of an investment. So you can see, I don't know if I want to write all this out. Actually, I might write it out and then I'll come back and talk about it. All right, so I've written out part C, so you don't have to sit and watch me write all this out. But essentially, at time t equals 1, the value stopped increasing momentarily, and then it began increasing again. All right. At t equals 4, the value stopped increasing and began decreasing. So that makes sense that it would hit its maximum when it stops increasing and begins decreasing. And at t equals 6, the value stopped decreasing and began increasing. So that was our minimum. Okay, I got one more example here. And then there's some practice problems. But the practice problems in this, I tried to pick some practice problems that are a lot like the homework. So I suggest that that you go through them and make sure you understand them just before you do the homework. All right, so let's take a look. We want to find constants a and b so that the minimum for the parabola, this parabola, x squared plus ax plus b, is at the point -1, 4. All right, so we're trying to, now this is kind of weird because we have a lot of variables here. We have x, but we also have this a and b, and we're actually trying to find the a and b values that cause this parabola to have a minimum at this point. Okay, so first of all, let's just find the derivative of this function. Okay, we can do this. We just consider a and b as constants. Okay, so we'll treat them like any other constants, like they were 2 or 3 or -8 or whatever. All right, the derivative of x squared is 2x, and the derivative of ax is just a, okay, because a is the constant. And then b is a constant, so we take the derivative of a constant and we get 0. Okay, so our derivative is 2x plus a. So if the function has a minimum at -1, 4, that's telling us that the derivative, okay, of at -1 is 0, because -1 has to be a critical point. We know this is a critical point. Okay, so that means that the derivative, f prime of -1, has to be equal to 0. Okay? Now, f prime of -1, if we just substitute -1 for x, we get 2 times -1 plus a, right? And then I want to solve for a. I want to find the a value that gives a critical point at -1. So this is just an algebraic equation. I'm just going to add 2 to both sides and I get 2 equals a. Okay, so that was easy enough. We found our a value. All right, now we also need to find b. And b is going to be determined because you see in the derivative b went away. So b is going to be determined by the value of the function. And we know that the value of the function at -1, the original function, is equal to 4. Okay, so if we put -1 in here, so -1 squared, and then now we know a is 2, so plus 2 times -1 plus b. Okay, so again we have an algebraic equation that we can solve. So we get 1 minus 2. Okay, so that becomes -1 plus b equals 4. I'm going to add 1 to both sides and I get 5 is equal to b. Right, so there's our b value. So that's our a and our b value. So what that's telling us is that the function f of x equals x squared plus 2x, oops, 2x, so just substituting 2 for a, plus 5, okay, that's our function that has a maximum at the point -1, 4. Okay. All right. So next thing here is just some practice problems. And I'm going to work out the practice problems. Well, the practice problems, I guess, are worked out in the completed notes. So I'm going to let you do those on your own. And if you have any questions about these practice problems, then make sure you come to office hours or contact me by email, and we can work through them. Again, like I said, the practice problems are very important in this because I tried to choose practice problems that were similar to homework problems. Okay, there's 2 homework sets. There's the Wiley homework and there's a supplemental homework for this section. So talk to me if you're having trouble with any of these practice problems, and we'll see you later.